All right, by popular demand, we're going to do a relative acceleration problem here, starting with this problem where we have a kind of a cam situation and we have a piston moving back, or this could be a valve. We've got a slider block moving this way. We want to find the angular velocity and angular acceleration of this wheel at this instant. So we want to know how this is accelerating and what is its angular velocity. So I'm going to start here and make some assumptions. Based on this movement going that way, I'm going to think it's probably a safe bet that our angular velocity is this way. And it's probably, and we'll call that angular velocity C. And I think it's probably safe to say angular acceleration is also that same direction. I don't know 100% that's the case, but I think that's probably a good place for us to get started. The first step that I'm going to do here is to try and figure out what's going on, is to also summarize any givens or finds. I think most of these are shown visually, so I'm not going to worry too much about that, but I can summarize them a little bit. I know that I already know VB, or sorry, given. I know VB and AB. I also know a lot about the acceleration directions there. The other thing that I could do, my goal is to find specifically what is our angular velocity and angular acceleration of this wheel. So I'm going to call it, I want to find alpha C and omega C. Those are my goals. I like to break these problems into two halves. So let's start with velocities first. The nice thing about using velocities is I can use the IC method for velocities and velocities only. Let's use that IC method to help us out. All of the action is actually happening here at on this member AB. So I'm going to actually draw that. Let me get a big, thick marker here. Make our AB going this way. So over here is B. Over here is A. Now I'm using velocities only, so I'm going to only throw my velocities on this thing. Now I know that this path is circular, right? A is rotating about this circular wheel. So I can say, hey, I know the direction of A. Velocity A is tangent to that wheel, right? This is our tangent direction. This is the tangent direction, and this would be the normal direction. So because that's our tangent direction, I already know the direction of VA. And they tell me the direction of VB. I also know it's a slider, so it's got to be that way. And I know the magnitude of that is 4 meters per second. So after I draw my kinematic diagram, I can actually just kind of ignore everything else, and let's just focus on that. So kinematic diagram first. Showing those velocities in those directions. I'm going to then find where my instantaneous center of zero velocity is. Using this method, I just draw a perpendicular line to each of my velocities. And using those perpendicular lines where those two perpendicular lines intersect is my instantaneous center of zero velocity. So there's my instantaneous center right there in the middle. And I can draw in now my dimensions that I have. So I know that this is going to be 400 millimeters, excuse me. And this is 100 millimeters here. Based on this, I can also determine the direction of this rotation, which is nice. I know that rotation. I'll need that a little bit later. This is my rotation omega AB. Is going to be going that way, but I don't know the magnitude of that yet, but I can find that in just a second. I know because I'm rotating about this instantaneous center, I can use my relative velocity equation. My relative velocity equation looks like this. I say, okay, my velocity B is going to be my velocity of my instantaneous center, which you might be yelling, Albert, it's 0. I know, I'm getting there. Is R times omega. Because I'm talking about my instantaneous velocity of 0, that's going to be 0 there. So I just say, hey, VB is going to be that R, this R B with respect to IC times omega AB. In this case, I can say, okay, well, omega AB is just VB divided by R. My velocity was 4 meters per second. My R, I make sure I have the same units, is 0.4 meters because it's 400 millimeters. So when I do that division here, move this over 1, move this over 1, this will be 10 over seconds. And you're going, Albert, wait, what happened to my units? Why did the ends cancel? Remember that these are rads. Rads are super cool and they're unitless. They don't need any friends. So we got 10 rads per second. We know that it's rotating this direction, which this is counterclockwise. So now I have omega AB. I could also find VA. Find VA. To find VA, what I'm going to do is say VA is just R times omega AB. In this case, R is going to be that 150, so I'll make that 0.15 meters times 10 rads per second, which is going to make this 1.5 meters per second. And we know that it's acting vertically straight down. All right, so now I found my velocities here, and that's where the IC method ends. We got to stop right there. Now we move on to accelerations. And this is the fun part about these problems is a lot of these acceleration problems are actually acceleration and velocity. So let's jump into the accelerations here. So our accelerations, let's get those on the page. So building that same kinetic diagram, but with accelerations. You know, acceleration AB is this way. And then let's talk a little bit about what's going on at A. A actually has two components. We look at A, we have two components. We have an A of N component, and we have an A of T component, right? As we travel in a circle, we're going to have those two components. We have A of N and we have A of T. Now AT, we're all used to this one. This is R times alpha, right? Where alpha is this alpha, which is, I'm sorry, in this case, this would be alpha C based on this calculation. So this is alpha C. This is where it gets a little hairy. This is not alpha C. This is alpha AB. Excuse me. We'll come back to this alpha in a sec. So that's alpha AC. A of N, right? A of N, well, we used to call this R squared over rho, but now we're super cool and we found a new way to say this. If we know that V is R omega and R is rho, this just looks like, well, R omega squared over R. We say that this just looks like R times omega squared. R in this case, we got to be careful is that RAC. So be really careful. This is going to be A of N in this case is 0.15 times omega C squared. So that's that. We don't know these two values yet. We're going to need to find those. So I'm going to leave these over here. This is going to seem kind of silly, but I'm going to leave these over here because we know these directions, but these are two unknowns over here, and that's not really going to help us solve. If we talk about relative accelerations, let's do our relative acceleration equation. Our relative acceleration equation, because we know what's going on specifically at B, let's use that again as our base. Let's use that as our base point. So we can say, hey, everything's kind of doing this rotating business about this point. So A is going to be equal to AB plus our relative components. In this case, we have two relative components. We have the relative component that's in the tangent direction, and we have the relative component that's in the normal direction. And this is the part why I kind of want to split this up a little bit. When we do these relative components, remember we're saying it's assuming this rotation about B. So when we look at the tangent direction for that, the tangent direction is going to be tangent to this rotation. We're saying we're rotating about A. I think it's safe to put this as this is our alpha AB, and we've already defined this as our omega AB direction in the previous problem. Remember, that's our 10 rads per second over here. This is still an unknown. And then we can say that the two components of that are defined this way. So it's tangent to this point. So this would be our relative component in the tangent direction, and then our normal component in the tangent direction, which would be acting this way, right? So this is where it gets complicated, and why students get a little frustrated with this part is we actually have two normal and tangent components. One of them is relative and normal and tangent based on our wheel, right? That's kind of the C part coming from our wheel. So that's these components over here. And we also have the relative components here. So I'm going to show that these are the ones in light blue. These are the relative. And let's talk about directionality for a bit. We know AB is acting to the right. We have defined A of A. Sorry, AB is acting to the right. We've defined A of A as two components here. We've got let's call it an A and C, which is acting to the right. You've got an A and T, which is acting down. Over here in the relative camp, we've got two components. We got one that's this one that's perpendicular here, and we've got another one that's acting along the line. Let's see if we can define those angles a little bit better. What do we know? Well, we know some about the geometry here. All right, let's look a little closer here. We've got a triangle that we can define here. If we're defining the triangle here, this vertical, let's try to define this angle here. Now, I could go really complicated on this, but you might be recognizing a friend of ours here. I don't know why it keeps drawing my triangles backwards. Doesn't like my drawings. Okay, let's see if we can flip-flop this. Nope, doesn't like my triangles. So here's my triangle here. And I love these triangles because this is a 3, 4, 5 triangle. I've got 300 over this way. I've got 400 this way. So this is a 3, 4, 5 triangle. And this is our angle theta. So using that information over here, I can define a lot of these directionalities here. This is also angle theta. So this is a 3, 4, 5 triangle like this. Make it very clear about which way is my directional vector here. And this is also a 3, 4, 5 triangle going this way. So this would be 4, this is 3, 4, 5 going that way. How do I know that? Well, if we're looking at our vectors, and I know that this is my tangent vector over here. I know that this is my tangent vector over here. I know that this is theta, then I also know that this is theta. So kind of using the sum of all these things, if this is 90 minus theta, working this backwards, I can go ahead and get to this as theta over here, which gives me that 3, 4, 5. So now I know the directionalities of all these things. I can start solving. Now, these relative components I can look up. This is not very hard, but it kind of follows that same idea. The tangent part is going to look like r times alpha, and this part is going to be that same, in this case, we're using alpha over here, which is alpha AB. And we've got this component over here, which is the r omega squared bit, right? If I can't find these equations, remember that this is all stuff that's in the back of the book. If I go to the equation list on the back of the book, I will get the relative velocities and accelerations given right here. So that's the A of t and A of r equations. Those are the ones that we're basically using right here. So changing the order a little bit. Okay. So knowing what we know about this, this is a known. We already know omega AB here. So this is a point that we already know explicitly. So I'm going to go ahead and solve for that. R times omega AB squared is going to look like, well, that's the R, just to be clear, that's our radius of our arm, or the length of our arm. Our total length of the arm is 500 because it's a 3, 4, 5 triangle. So it'll be 0.5. So it'll be 0.5 times omega AB, which is 10 rads per second squared. So squaring that, that's going to look like AB is 50 meters per second squared. There's my value right there. And I know it's acting at this triangle here. Like that. This relative part, I still don't know, but I know the R there. In this case is that same R, so it'll be 0.5 times alpha AB. I know that it's acting in the 3, 4, 5 direction. I got alpha AB acting to the right. And I got these two components, A and C, which is acting this way, and A and T, or sorry, this should be ATC, because it's the tangent part with reference to C. I could even just do it something like that. ATC, that's acting down. All right, so thinking about this, this is an unknown. AB is known. This is an unknown. This is unknown. We got to find those unknowns here. So we're missing something important here. If I look at this, I've got 3 unknowns here. I'm missing a velocity. Let's see if I can simplify this a little bit. What I'm missing here is this velocity, omega c. I'm looking at that and going, I missed something here. This is an important detail. I need to get that omega c. Let's go back to velocity for a bit. I know that this is a little tricky. I hate jumping around, but this is the fun part about doing problems live. We had omega c. We're missing omega c. So I'm going to write that really big. Why are we stopping here? We missed omega c. Darn it, Albert. What do we do? Let's see, what can we do? Well, if we want to find omega c, want to find it that how fast that wheel is rotating, let's go back to that instantaneous method for a sec. We found out what the rotational velocity is, but we never figured out what VA is. Let's find VA. Let's find VA. Now we know VA is going to be R times omega c. Now in this case, we know R to be the radius of our wheel, at 0.15. 0.15 times omega c. Let's find VA. But we also know VA could be calculated from using the instantaneous center. because we know that member AB is rotating about that instantaneous center of zero velocity right there, VA is actually pretty easy to find, or we found it right here. So all we need to do is find omega C. So omega C looks like VA divided by 0.15, which is going to be 1.5 meters per second divided by 0.15. Move this decimal place over twice. This looks like 150 rads per second. Remember that this is meters, so those meters cancel. This is going to be super rad. We've got 150 rads per second. So in this particular case, now that I have omega C, I can go back to solve this one, right? I've already figured out what these two components are. I know A of N looks like R times omega C. So let's plug that in. I can find this value. A and C looks like R times omega squared. Remember that I'm finding this acceleration, this normal acceleration, is the normal acceleration because I'm rotating about a wheel, right? I'm finding this component here. So I'm going to find that A and C. What's my radius? Radius is 0.15. Omega, in this case, is 100 rads per second squared. Sorry, 100 rads per second. And then I'm squaring this. So squaring this twice, I've got 4 zeros. So this will be 1050, in this case, meters per second squared. Because this thing is rotating so quickly, oh, sorry, this should be 100, excuse me, 300. Small math error here. This is what happens when you try to do work without lunch. 1.5 divided by 0.5 here. This is just 3 rads per second. That makes a lot more sense. Sorry about that. Made a simple math error here. This is 3 rads per second. I was wondering why this value seems so off. So coming back to omega C here, omega C is a much different answer. I was like, why is this so large? If you have a gut reaction that something is wrong, it's better to stop and check your work then get to the answer and go, what happened? Times 9. Okay, this makes a lot more sense. This is 1.35 meters per second squared. Remember that this is rads per second, and this is meters, so our answer is going to be meters per second squared. So now I have this value over here. I'm just going to go ahead and replace that A of N with 1.5 meters per second squared, going to the right. In this particular case, I know A of B also. Remember, A of B is given to us. A of B is given over here as 2 meters per second squared to the right. So I know all of this information here. What I'm missing is alpha AB and the tangent component over here, which I know this tangent component looks like RC times alpha C. Now alpha C I don't know, so these are my unknowns. So if I'm looking at this, the real question is, do I look in the X direction or the Y direction first? Do we look in the X direction or the Y direction first? In this case, looking at the unknowns, this unknown is going to show up in both the X and the Y, but this one only shows up in the Y. So I'm going to look at the X direction first. And when I look at the X direction, this is what I'm going to see. I'm going to see 1.5 meters per second moving to the right. So that's positive. Over here, this doesn't, this RAC only works down, so that doesn't count. I've got 2 meters per second moving to the right. So that's going to meters per second squared moving to the right. So that's going to be positive. I've got this part, which is negative. It'll be 0.5 times alpha AB times the ratio. In this case, it's 4/5. And then I've got this point, I've got 50. And then this ratio is going to be 3/5. And that's positive here. So simplifying this will look like 0.1. Canceling out the 5 here, this will be 10. So I've got 1.52 minus 0.4 AB, alpha AB, excuse me, plus 30. Simplifying this, I've got negative 0.4 over here, alpha AB, 1.5 minus 32. So alpha AB looks like 1.5 minus 32 divided by negative 0.4. Let me just do that calculation really quickly. Divided by 0.4. This is going to be 76. Now in this case, I remember that all of these are meters per second squared, and this is radius in meters. So I get 76.6 rads per second squared because the meters cancel out. Thinking about that, coming back over here, remember that when I'm finding this alpha AB, I'm talking about how does this rotate. Because I got a positive answer, I know that it's going in this direction. This is about 76 rads per second squared. So now I've defined A of N. I've got A of T. Let's go in and calculate our last bit. We want to find that AT part. This AT part over here, remember this is our AT from our wheel. Let's go in the Y direction. So in the Y direction, I have RC times AC. And then the 2 meters per second doesn't contribute because it's only in the X direction. I've got the Y direction here, which I've got 0.5 times my alpha AB, which I just found is 76.6. In this case, we're looking at the vertical direction. So this is negative 3/5. Right? The vertical part is 3/5. It's going down, so it's negative. And then I also have a negative number over here for negative 50 meters per second squared, and this is 4/5. So simplifying this, I could just say, hey, alpha AC looks like these two values, and they're both negative, so that clues me in that my answer here is negative. I guessed the wrong direction for alpha. That's okay, not a big deal. I've got 0.5, so I'm just going to call this 0.5 times 76.6 times 3/5 plus 40 because I got the negative out here. I'm not going to deal with that. RC is the radius of our wheel, which is 0.15 meters. Up here we have meters per second squared. So alpha AC is going to be rads per second. So 0.5 times 76.6 times 3/5 plus 40, divide everything by 0.15. I get a alpha, which is incredibly large here, rads per second squared. Let's double check my work here real fast. Yep, that's correct. So that's those two components. So for this thing is accelerating, and this was negative. So remember, that means it's opposite to what we guessed. We guessed an alpha direction. We assumed it was accelerating in the same direction that it's rotating. We actually got this backwards. So it's not counterclockwise like we drew. It's actually clockwise, shocking everyone to their core. There is alpha C. Now we were asked specifically with this problem to find alpha C. Let's go back to our finds. Our goals were to find alpha C and omega C. We forgot to do omega C. Remember, we had to come back to omega C. That's this calculation here. We did come back and get omega C, which we did need to find alpha C in this case. When you do this, I want to also think about direction. We said omega C was going in the same direction counterclockwise as we guessed. In this case, we said clockwise rotation here. This process is a little bit longer, but it's just a reminder. This is the tricky part here. One thing I would really focus on is getting that N and T coordinate here. So I'm going to pause the recording here and answer questions. I'll come back and answer those as well.